My name is Ali. Today we're going to talk about how to use FFTs to implement DFTs on FPGA. Since you are here in this class, I'm assuming you like FFT, DFT, and FPGA and all of them, and you're interested to know more about how to put those guys on FPGA. I'm also assuming that you have a little background with math that is going on here. So I'm going to throw it a little fast, and for the sake of time, I already write all the equations. So DFT, discrete Fourier transform. Why we use it? We use it to transfer a discrete signal in time domain into frequency domain. Why? To find out the characteristic of your signal, where the energy is sitting, and what frequencies or what wideband we have. They can be for various applications like wireless systems or image processing. And how it's done? Here's a theory. You have your samples with the length of n. You put it in the sum, multiply with exponential. You end up having your values in signal. In frequency. What's wrong with this? Nothing. It gives you a very accurate answer. But if you want to calculate this, you have to multiply a matrix of n by n with a vector of n, which makes a computation time high with big O of n squared. It's very expensive on an FPGA. It takes a lot of your resources. What's the solution? We can move these guys around and use some properties of FFT to make that big O n log n, which is way better. So how are we going to do that? First, that xn, we're going to rewrite it as even parts and odd parts, which is the even samples and odd samples. And we're going to write that equation like this. It's a little scary, but there is nothing magic going here. I just rewrite it and then factorize one exponential, and this guy end up being the same. So I call this guy even, that guy odd, and we end up with a nice equation like this. So far we didn't save anything. We just moved something around and renamed a couple of things. But that even part and odd part, they have two very interesting characteristics. EK plus N2 is equal EK, and OK plus N2 is equal OK. Also for this guy, e to the minus 2 pi I n k plus n2. It's a basic math. You probably had it in your first grade. It's minus e minus 2 pi I n k. Just a sign will change. So I'm going to write that equation using these guys. I'm going to end up having these two. We go here, we go there. So xk is that, xk plus n2 is that. What does it mean for me? What it's saying to me is, if I calculate xk with ek and ok, for k plus n2, I don't have to recalculate everything. I just flip a sign, and there you go. I have a xk plus n2. Here's an example. It's a DFT of length 8. Instead of having length 8, I divide it to n over 2-point DFT. You have even samples coming into the first one, E0 through E3, and then odd samples coming into the second half a point DFT gives me E0 to E3. If I add them together, like with this, just keep in mind that that sign is different for k plus n2. I can calculate my x0 through x7 only using these two half a point DFTs. This algorithm, I forgot to tell you, it's called radix 2 case of Cooley-Tukey. It's recursive. You can divide this half a point DFT to two quarter point DFTs and make your others and multiply it even less. And that's how it's done. Thank you for watching.